Let's continue to answer the question, how do I use tables, diagrams, graphs, and equations to represent quantities that vary together? If you look at workbook page 213, we have another problem with constant speed, which is what we talked about in the last lesson. Suppose a high-speed train travels at a constant rate between Greenville and Orange Lake. T will be the number of minutes elapsed, and D will be the number of miles the train has traveled. So T is for time, D is for distance, but the unit that we're going to use for time is minutes, and the unit that we're going to use for distance is miles, because remember, we always want to make sure we include units of measure when we label our variables. The variables D and T vary together. Their relationship is represented by the equation D equals 2.5 times T. So that means distance is equal to 2.5 times the minutes, or times time. Let T be the independent variable, D is the dependent variable. So again, the time is independent, the distance is going to depend on how much time the train is traveling. So let's first complete our table. Remember, our equation was D equals 2.5 times T. That means we have to do 2.5 times the time. Well, if the time is 0, 2.5 times 0, well, that's 0. If the time is 1, we would have to do 2.5 times 1 minute, which of course is 2.5. If it's 2 minutes, we'd have to do 2.5 times 2, which is going to give us 5 miles. If it's 3 minutes, well, then we have to do 2.5 times 3, and that's going to give us 7.5 miles. If it's 4 minutes, distance is equal to 2.5 times 4, and that's going to give us 10 miles. And we could continue this procedure where you multiply the time by 2.5, and you can complete the rest of the table like so. Now what we're going to do is we're going to graph those points from the table on the graph on the right. So let's see. First, I'm going to change the color. Let's go with purple here. Obviously, if 0 minutes have passed, then we have 0 miles traveled. If 1 minute has passed, now we're at 2.5 miles. So 2.5 would be somewhere in between 2 and 3. I'm going to estimate it to be right about, right about here. Not perfect, but that's okay. And then 2 minutes would be at 5 miles, so that would be right here. And then 3 minutes would be at 7.5 miles, so 7.5 is between 7 and 8. So that would be right about here. And let's see, 4 minutes, now we're at 10 miles. And 5 minutes, we're at 12.5 miles, so that would be in between 12 and 13. And then 6 minutes, now we'd be at 15 miles. So, does it make sense to connect the points on the graph? If so, connect them. And yeah, I think it does make sense. It looks like a nice straight diagonal line. Yes. Draw a unit rate triangle on your graph. So let's see. Remember, the unit rate triangle shows us how much for 1. So for 1 minute, we go up 2.5. For another minute, we go up another 2.5. For another minute, we go up another 2.5. And each time, we're increasing it by 2.5. So using that unit rate triangle, can we answer this question? What is the speed of the train in miles per minute? How many miles does it go in 1 minute? What's the unit rate? Well, it looks like in 1 minute, the train is traveling 2.5 miles. So it must be 2.5 miles per minute. And we can see that from the unit rate triangle. Remember how we said the unit rate triangle shows you the unit rate by looking at the vertical height. Now that was an example of a constant rate, constant speed. But not all equations are going to end up being constant. Take a look at workbook page 214. Superhero Supplies Inc. produces different superpower soups. That's kind of cool. In the factory, each type of soup flows into a different vat. Let T be the number of seconds elapsed. Let V be the number of liters of soup in the vat. So again, we're labeling our variables, we're including units of measure. T is for time, in this case in seconds. V is for the number of liters of soup that are in the vat. So for each vat, V and T vary together, and they're related by an equation. So remember, varying together means as one thing changes, it's going to affect the other. So take a look at all the different vats. We have vat 1, where you'll have a soup for super strength. Vat 2, there's soup for X-ray vision. Vat 3 is a soup for flying. Vat 4 has a soup for lightning speed. And Vat 5 has a soup for invisibility. And take a look at all the different equations. Every equation is a little bit different. We're going to look at a couple vats together, and then you're going to look at some on your own, and you're going to determine whether you actually have a constant change. So let's look at vat 1. Vat 1, remember the equation was V equals T squared, or the number of liters in the vat is equal to the number of seconds squared. So let's use that equation to help us complete this table. If I have V equals T squared, if I have 0 seconds, that means V, the number of liters, is equal to 0, which is the time, in seconds squared. And obviously 0 squared is just 0. So if 0 seconds have elapsed, then I've got 0 liters in my vat. But what if 1 second has elapsed? So V is equal to 1 second to the second power. Well, 1 to the second power is 1, so V would be equal to 1. If 1 second has elapsed, then there's 1 liter of the soup in the vat. Well, what if it's 2 seconds? Now I have 2 to the second power, which 2 to the second power is 4. So now if 2 seconds have elapsed, I've got 4 liters of soup in my vat. Let's keep going. What if it's 3 to the second power, 3 seconds to the second power? That's going to be 9. So if 3 seconds has elapsed, then I've got 9 liters of soup. V to the 4th power now. I'm sorry. V equals 4 to the second power. 4 seconds has elapsed, and that means I now have 16 liters of soup. And you can continue to complete the rest of this table using, that equation V equals T squared. So then this would be 25, this one would be 36. And now what we're going to do is we are going to graph or plot the points from vat 1 onto the graph over here. And again, our independent variable is the seconds, so that's one on the x-axis. We have the dependent variable, which is the liters of soup in the vat, and that's on the y-axis. All right, so 0, 0, that's right about here. And then 1, 1, that's right here. 2, 4, that's right here. 3, 9, that's here. 4, 16, it's right up here. 5, 25 is right here. And 636 is all the way up here. So let's see. Connect the points if it makes sense to. Yeah, I think we could connect the points, but if you notice, it looks like we have a little bit of a curve to it. Do you notice that? It's not a completely straight line. There's a curve going on there. So is the soup flowing into vat 1 at a constant rate? In this case, no, it isn't. The reason you can tell that it's not flowing at a constant rate is because when you graph it, you are not seeing a straight line. Also, look at the table. You're not increasing by the same number each time. I'm going to just erase this real quick. Here you're going up by 1, and now you're going up by 3, and now you're going up by 5, and now do you see how each time you're not increasing by the same amount? So no, it does not increase at a constant rate the graph isn't a straight line. Now let's take a look at VAT3. This is on page 215, so I'm skipping around a little bit. I'll let you do VAT2 on your own. VAT3 is V equals 5 times t plus 3. So let's see. If I were to fill in my table, I'm going to use my equation to help me. Obviously, V equals 5 times the time, which is 0, so 5 times 0 for seconds elapsed, plus 3. Well, 5 times 0 is 0, plus 3, that means if 0 seconds has elapsed, there's 3 liters in the vat? We'll have to think about why that may be. How could there be 3 liters in the vat when 0 seconds has elapsed? Let's see, V equals 5 times 1 plus 3. Now we're putting 1 in for the time, 1 second. So 5 times 1 is 5, plus 3 more. Now we're up to 8. Let's see, now we'll put in 2. V equals 5 times 2 plus 3. 5 times 2 is 10, plus 3 is 13. I'll do the same thing for 3 seconds. 5 times 3 seconds is 15. 15 plus 3 is 18. And you get the idea. You can use this equation to fill in the rest of the table to figure out, after how many seconds has elapsed, what number of liters would be in each, would be in VAT3. So let's see, we'd have 23 here, we'd have 28 there, and if 6 seconds has elapsed, now we're up to 33. So all you have to do is plug the seconds elapsed in for t, and then solve your equation for v. So now, let's try graphing this. Let's plot these points on our graph. And you're going to be plotting this for VAT2 as well. So if I were you, maybe I would use different colors, or maybe use different lines, so you know the difference between which one is VAT2 and which one's VAT3. Maybe you want to use like a dashed line, or one that's a little more bolder, thicker. That's up to you. I'm going to use different colors. So I'll just use purple, but if I were to do VAT2, if I were to do VAT2, I would probably do like a different color to mix it up. So let's see, 0, 3, well that's right about here. If it lets me graph. Oops, still had the eraser on. That would be why. There's 0, 3, and then 1, 8 is here. And then 2, 13 is here. And 3, 18 is here. 4, 23 is here. And 5, 28 is up here. And 6, 33 all the way towards the top here. And you can see that if I were to connect it, it forms a straight line. Check that out. And also, we could even make a unit rate triangle here. You can see that for every one that we go over, we're going up by 5. We're increasing by 5 every time. Over 1, up 5, over 1, up 5, over 1, up 5. So is the soup flowing at a constant rate in VAT3? Yes, it is. It's flowing at a constant rate because I can see my straight diagonal line, and I can also see that I'm increasing by 5 every single time. 3 plus 5 gives me 8, 8 plus 13, 8 plus 5 gives me 13, 13 plus 5 gives me 18. So this one is increasing at a constant rate. You can see that it's increasing by 5 every time. Look at the unit rate triangle. It's increasing by 5 every time in the vertical height, and it's forming that straight diagonal line. Now, for number 15, I want you to think about this. What does the 5 in v equals 5t plus 3 tell you? What does that 5 tell us? We said we increased it by 5 every time. Well, in this case, the 5 is telling us the rate at which, it's being poured into the vat. The soup is being poured into the vat at a specific rate. The 5 tells us the rate at which the soup is flowing into the vat. In this case, it's flowing at 5 liters per second, because seconds was the unit. So 5 liters per second. That's our unit rate, 5 liters per second. So our coefficient is telling us the unit rate. And we saw that in previous lessons. The coefficient tells you the unit rate. How about the 3 though? Notice it's got a 3 in there. We started with 3. Look at the table. Remember how we said, oh, even though 0 seconds has elapsed, somehow we have 3 liters in the vat? And look at your graph. Do you see how it's starting at 0.3? It starts right here on the y-axis. That is probably telling us that there must have been 3 liters in the soup. 3 liters of soup already in the vat before more was being poured in. Maybe it was left over from the day before. I don't know, but there was. I'm going to write this down. The 3 tells us the number of liters in the vat to start. So there must have been 3 liters already in the vat before more soup started flowing in. So that's why even at 0 seconds we had 3 liters in the vat, and that's why it's not starting at 0. Most of the other ones started at 0 on the graph. This one is starting right here on the y-axis, and that's because it starts with 3 before we even started pouring more soup in. Okay, takeaways. So when you want to figure out, what the different values are in our table, you can plug values in the equation, which is what we had done, for the independent variable to determine the values for the dependent variable. So if our independent variable was seconds, we plugged in the number of seconds into our equation, and then we were able to figure out the, in this case, I think it was liters of V, we used V, to determine the dependent variable. And then you can graph, from your table, you can graph those ordered pairs on the coordinate plane. And remember, constant change is the rate of change that increases at the same rate. It forms a straight diagonal line on the coordinate plane. So remember, if it's going to be a constant change or a constant rate, you're going to see a constant increase in your table. You're also going to see a straight diagonal line on your graph.